Welcome to these videos on the foundations of graph algorithms. Graph algorithms are normally studied towards the end of a course on data structures because they use all the simpler data structures that have been covered earlier, from arrays and linked lists, stacks, queues, hash tables, priority queues, to trees and so on. So please make sure that you have a basic familiarity with these other data structures which are going to be directly used in our implementation of graph algorithms. In case you are wondering about the comic here, this depicts the well-known traveling salesman problem, which you can learn more about once you understand graphs. The salesman depicted here needs to sell his products by traveling to a bunch of cities across the United States. And he's trying to figure out the best order in which to visit each city so that the total distance he needs to travel is minimized. He's trying really hard to come up with the best route, but he's unable to do better than an exponential time algorithm. In fact, no one has come up with a better than exponential algorithm for this problem. The other salesman here has decided to be lazy and is selling all his products on eBay in a constant amount of time, and he seems to be doing quite well. The overall structure of these videos on the foundations of graph algorithms is the following. I'm going to begin with a gentle introduction to graphs, explaining the terminology and basic concepts that are needed to reason about graphs. I will do this by taking a single problem called the Eulerian cycle problem, which led to the invention of graphs in the first place. In my opinion, the best way to understand any idea is to see how it was invented by peering into the mind of the original inventor to draw both inspiration and a deeper understanding. Once we solve this problem, we will attempt to take the solution and make it into an algorithm that can be run on a computer on any graph. For this, we need to understand how graphs in general can be represented on a computer. Almost all the problems on graphs given to us will require the computer to first explore the graph systematically, starting from one point, to discover its structure and then to use that information to solve the problem. So we will look at a general graph exploration or search algorithm, and we will find something that even most computer science students miss when they study graphs, that all the graph algorithms they are studying, from breadth first search to depth first search to Prim's algorithm and Dijkstra's algorithm and even A star for that matter, are just variants of this general graph search algorithm. So by understanding this general algorithm well, we don't have to struggle to memorize 5 or 6 different disconnected algorithms. We just have to understand one general algorithm clearly and see how most of the other algorithms are just variants of this general algorithm. So this will form our basic graph algorithms toolkit. We will then understand some popular extensions of these graph algorithms to make our graph algorithms toolkit more sophisticated. And with this expanded toolkit in our pocket, we will be ready to tackle most graph problems in technical interviews. Rather than solving a bunch of disconnected graph problems, it's better to master graph algorithms in this structured manner, where you would be able to discern clearly what the various patterns underlying the algorithms are. Note that the foundation videos will cover the topics shown here in pink. The live classes and more advanced videos would cover some more details within these topics and also take up the topics shown in gray. In an interview setting, when you're given a problem, you will have to first think about whether the problem can be modeled as a graph problem or not. In some cases, the problem may be an explicit graph problem, in which case there's no modeling needed. But in other cases, you may have to model the problem first as a graph problem in a way that allows you to whip out your toolkit to solve the problem. In some cases, our simple toolkit may be sufficient, but in other cases, we may have to draw upon our extended toolkit. And once you can see what algorithm in our standard or extended toolkit would solve the problem, you would then code it up.